So now that we've seen the quantum numbers, each electron needs its own, what we need to do now is start assigning the electrons to the atom, all right? And with like all things, all right, electrons will go usually as close to the nucleus first, and then they get farther and farther away. And Bohr saw in the last section that the energy of an electron was really just depends on n. And we did some stuff where there was 1, 2, 3, 4, and we did absorption and emission kind of stuff. And all of those were really just based on n, the shell number. Bohr's model worked really well for anything with only one electron. So hydrogen and helium plus 1, awesome, Bohr's awesome. However, when you have more than one electron, Bohr's theory didn't work very well. And from quantum mechanics, they found that the energy of electrons is better described through both n and L. So what we're going to do now is start seeing what the n plus L rule is all about. And when we put electrons around atoms, this is what we use. We always start with the lowest n plus L, and we work our way up to the highest n plus L. And if you've seen chemistry stuff before, you maybe have seen like electron configurations, 1s2, 2s2, 2p6, this kind of stuff. Those 1s2, 2s2, those are using the n plus L rule. So we're really going to see in this chapter like where that stuff comes from and why n plus L works and stuff. And we'll see stupid diagrams like this with the anyway, I have a very weird sense of humor. But anyway, notice there's 2 cats on each one of these little orbital things and stuff, and that's kind of the n plus L rule. But anyway, obviously having too much fun with my teaching job. So anyway, the n plus L rules we're going to get into. So we're going to use the n numbers, which are just whole numbers. And remember, L values a lot of times get a letter associated with them. So S, P, D, F, this kind of stuff. So, punchline of this slide, in the old days with Bohr, energy was just depending on n. Like R, H, and C were all constant, so it just depended on n. But in the modern day, from modern quantum mechanics, the energy actually depends on both n and L. So when we talk about the n plus L rule, that's literally using the n value with the number L value to see how this works out. So, if you have a hydrogen atom, then all of these different orbitals are the same energy. So look at this little picture right here, which is going to be part of the video. And right now, 1s is this level right here, and 2s and 2p, which both have the same n number. Remember, the number in front is n. They're the same energy. Here's the 3s, 3p, and 3d, the 3 train tracks Wes asked about. They're all the same energy. And here's the 4. By the way, each blue line is an orbital. So we saw how when p means L equals 1, m sub L negative 1, 0, plus 1, 3 m sub L values on the 2p subshell. So these are literally like the houses on the streets right now. First street, second street, third street. Second street has 2 houses, third street has 3 houses, etc., etc. And right now, if you look at just n, all of those houses with their individual rooms shown would have the same energy. However, in the actual world, the n plus L rule plays a factor. So let's do some n plus L calculations for 2s and 2p. Well, n, L, n plus L. If we have a 2s subshell, what's the value of n? 2. It's literally the number in front, so that's not supposed to be hard. All right. If you have an s, what is the value? What is the number value of L? 0. That's right. So n plus L literally means 2 plus 0, 2. All right, that's all n plus L means. Now, for 2p, n is also 2. P means L equals 1. N plus L, 2 plus 1, 3. All right? So these are how you calculate N plus L values. It's literally adding them together. And smaller N plus L will be lower, and higher N plus L will be higher. Lower N plus L means closer to the nucleus. Higher N plus L means farther from the nucleus. Yeah.
Instead of lower and higher, you mean lower and higher energy? Right?
No, lower and higher N plus L, Wes. So 2 versus 3. Smaller N plus L would be 2, okay?
Okay.
And higher N plus L would be 3. It's so simple, it's hard. So I'm glad you asked, all right? Yeah, literally, look at these numbers right here. 2 is smaller than 3, all right? So 2 would be closer to the nucleus. 3 would be farther from the nucleus. So on this diagram, the nucleus, right down here, under 1s, all right? And when I push this video here pretty soon, it's going to show how N plus L changes the landscape quite a bit. So instead of having 2s and 2p on the same energy, we're going to see here that 2s is going to be lower because it literally has a smaller N plus L value. And the higher N plus L will be higher in energy, farther from the nucleus. Other questions on that? Okay. Sometimes you can have a tie, and then in those cases, lower N will be higher energy. I'll talk about that in a little bit, but I want to show this video first here.
In a single electron atom, hydrogen, subshell energies depend only on the subshell's principal quantum numbers. In a mini-electron atom, the presence of electrons in one subshell affects the energy of other subshells. Consequently, the subshells are not filled simply on the basis of the principal quantum number.
Now, what this means is that at first with Bohr, 1s was down here, both of the 2s, 2s and 2p up here, same energy, and all the 3s were the same energy, all the 4s, etc., etc. However, in the actual quantum mechanical model, it's not about N, it's N plus L. So notice here, this is what we just did. We saw that N plus L for 2s, 2 plus 0, 2, is literally a smaller number than 2 plus 1 for 2p, which is 3. So 2s lower N plus L than 2p. That's literally how they find these ordered. So when you start putting electrons in atoms, they're going to go to 1s first, closest to the nucleus. 1s gets filled, the next one up is 2s. After 2s is filled, you go to 2p, and then 3s, 3p, etc., like that. It's all from the N plus L rule, which is so simple. It's weird to think about, but it really is that simple. Questions on that? Now, something strange happens when you get to certain quantum numbers. So, let's see here. What would be a good example of this? 3 plus 1. Yeah, let's look at 4s and 3d, all right? And just like before, N, L, N plus L, okay? So for 4s, what is the N value? 4, good. For 4s, what is the L value? 0. So N plus L, literally 4 plus 0, 4, all right? You know, this isn't going to work. Let's do 3p. I'm sorry. My bad. Let's do 3p. I'll show you why I'm doing 3p instead of 3d in a little bit. For 3p, what is the N value? 3. Good. For p, what is the L value? 1. So why I wanted to change here is because 3 plus 1, the N plus L value here is 4 as well. So this last part says that if you have a tie, if you have the same N plus L value, like here, the lower N will be lower in energy. So remember that N equals 3 for 3p versus N equals 4 for 4s. That's why 3p is filled in before 4s, all right? 3d would have had N plus L equals 5, and that wouldn't have worked, but there's a reason why I was using N plus L 5, but anyway, that's a different story. So this is showing how these things get filled in, all right? It's all about lower N plus L. 1s gets filled in first, 2s before 2p, because 2s has N plus L of 2 versus N plus L of 3 for 2p. 3s also has N plus L equals to 3, but 2p gets filled in before 3s because it has a lower N. If there's a tie, lower N first, higher N last. Any questions? Sweet. This is why, if you have seen chemistry before, it's always 1s first, 2s next, 2p. It's all about the N plus L rule. All right? So you're seeing here the quantum mechanical derivation, if you will, of why 1s is first and 2s, et cetera, et cetera. So, cool. Anyway, too excited here, I know. This is called an Aufbau diagram. And an Aufbau diagram is one way that you can quickly figure out the orbital filling order for electrons, all right? And you know what? I'm going to put this, well, I'm just going to erase some of this, yeah. You all know there's no school on Wednesday, so. To build an Aufbau diagram, start with 1s, go 2s, 3s, 4s, 5s, as high as you want. Now, as we've seen, it goes S, P, D, F, G, etc., etc. Skip 1 and go up. 2p, 3p, 4p, 5p, and you can go up higher like this one did if you want. Skip 1 to go to 3d. So notice I'm skipping 1 here to get to the higher ones. 4d, 5d. Skip 1. 4F, 5F, 5G would be right there, by the way. But anyway, if you have something like this built, all right, then you can literally have arrows going through them like this. And I'll show you why these arrows are kind of cool. These arrows are technically N plus L arrows. So the first one is N plus L equals 1. The second one is N plus L is 2, N plus L equals 3, etc., etc. But it doesn't really matter for you because what it shows you is the order in which you fill electrons. The first arrow only has 1s, so you fill that one in first. Then it's like you skip down here to the next arrow, 2s is next. Then you skip down here, 2p is the next one you fill in, but then 3s after that. Keep going. 3p, 4s, keep going, 3d, 4p, 5s, etc., etc. There's different ways to figure out this electron filling order, all right? And one way is just to use N plus L values. But Aufbau diagrams can be really helpful. You can see I built one right there. You can do it yourself on a piece of paper, or of course, you can just print off something like this, which is fine. But it's very helpful because it tells you where you fill electrons in. What it means is that you always fill in the 2p orbital before you fill in the 3s. And you fill in the 3s orbital before you fill in the 3p's. And 3p's before 4s's, before 3d's, etc., etc. Aufbau means building up, apparently in German. I don't know. And Bohr and Pauli came up with this idea. And at first I was like, oh, you can really use the periodic table, which I was teasing Jonah with in the break a little bit. But really, the Aufbau diagram is a nice way to do the electron filling order if you want. And you just literally follow the arrows back and forth. I have a handout on the website that's an Aufbau diagram. It's, I think, a little fancier than this. But anyway, it's very easy to build up. You just always start at 1s, and then you just skip. So S, P, D, F, 5G would be right there. 6, H would be the next one. But you don't really need it, as we'll see. Any questions? Okay. So what we're going to do now is start actually putting the electrons in the orbitals and the subshells, all right? And there's two main ways that this is done in chemistry. And the most common way is what they call spectroscopic or SPDF notation. And when I said earlier like 1s2, 2s2, that really is spectroscopic. Now, 1s is our good old NL notation. And again, the number outside is just the N value, and the letter corresponds with the L value. I kind of erased the L value there, but Hopefully this is becoming more familiar to you. And the superscript on the right-hand side represents the number of electrons that go inside, all right? So 1s1 would be one electron in a 1s subshell, and that's totally fine. So 1s1 would be that. And don't use parentheses around the 1s's or anything like that. They're just using it like that. Hydrogen has one electron. And using off-bow or n plus l, the first orbital to be filled in is the 1s. So hydrogen with one electron, we'll put one electron in the 1s right there. 1s1 is the electron configuration for hydrogen. Woohoo! So pat yourselves on the back. One atom down on the periodic table. The other ones are coming up here pretty soon. If I said write the electron configuration for hydrogen, you would literally write 1s1 like that. Superscript 1 to show it's one electron. It's in the 1s subshell because that's the first one to get filled in on the Aufbau diagram or anything like that. Pretty chill. Now, helium is number 2, right next door. Helium has an extra electron. Now remember that you can always have a spin up and a spin down. So helium would be 1s2 because you can have 2 electrons in each orbital and each subshell, stuff like that. So for helium, the spectroscopic notation with 2 electrons would be 1s2. Now, this little picture right here is what they call orbital box notation. Orbital box is a nice way to see if you have something that's paramagnetic or diamagnetic. So earlier when we had hydrogen, you could write 1s under a box or a line is fine. And there's one electron, so you would write like one arrow like that. This would be the orbital box notation for hydrogen. Helium has 2 electrons. And remember that m sub s means spin up or spin down. So for helium, 1s2, you'd have one up electron and one down electron. Yeah.
So does that mean that an odd number of electrons makes it paramagnetic?
Paramagnetic, well done. Yeah, that's okay. Oh, you math guy, Wes. Yeah, paramagnetic, no problem. Paramagnetic, absolutely. Wes brought up one of the big things. If you have an odd number of electrons, it's always going to be paramagnetic. I'm not even extended, Wes. And most of the time for figuring out the elements, most of them are paramagnetic. So if you have to guess, all right, there's a heck of a lot, even a lot of the even ones are going to be paramagnetic, and I'll show you why in a little bit. But definitely all the odd ones absolutely will be paramagnetic, man. Good. It's all about patterns, man. These are the four electron quantum numbers for the 2 electrons in helium once again. N equals 1, L equals 0 would be 1s, a single orbital. This is an orbital. This little box right here, that's really what it is. And each orbital can hold 2 electrons. One of them spin up, one of them spin down. So the up one, I would argue, is the positive 1/2. And the down one, I would argue, is the negative 1/2. Any questions? Okay. This diagram is a little bit fancier. It's kind of like the one we looked at earlier when the field was applied. So each of these little squares, the purple squares, is like one of the boxes, and they represent an orbital. Now remember, the 1s house had 1 room. The 2s house had 1 room. But the p houses have 3 rooms, 3 m sub l's. So all of the p's mean L equals 1. And if L equals 1, m sub l minus L to positive L minus 1, 0, plus 1. So all of the p subshells are going to have 3 of these little boxes. And those represent m sub l, negative 1, 0, plus 1. Negative 1, 0, plus 1. The d's have L equals 2. So their m sub l's, negative L to positive L, negative 2 to positive L, negative 2, negative 1, 0, plus 1, plus 2, 5 orbitals in the D subshell. All of the D's have 5 of them. Notice that the F's with L equals 3, negative 3 to positive 3, 7 orbitals on those. So this is a way then you can use to assign different electrons. First electron, down in the 1s. Second electron, each box holds 2 electrons, so 1 up, 1 down, you're good to go. But when we get to the third one, we're going to have to start putting electrons up here because then the S's are full, etc., etc. We're going to keep on. Any questions? All right. So the periodic table has its form because of the orbitals, the subshells that we're filling in. And Jonah, this is what I was kind of alluding to earlier when I talked to you. The 2 left-hand columns, 1A and 2A, with helium over here, by the way, for this argument, those are S subshells, all right? So hydrogen and helium, if we put helium right there, would be 1S subshells. Lithium and beryllium, we're going to see 2S. And sodium, magnesium, 3S, 4S, 5S, etc. You can literally use this number to figure out what the number is that goes in front of the S. Now, the 6 columns on the right, not helium. Helium goes over here for this conversation. These are the P subshells. So we're going to be filling in P electrons over here. Remember, there are 3 orbitals in P, L equals 1, so M sub L negative 1, 0, plus 1. And each of those holds 2 electrons, 6 electrons total. 1, 2, 3, 4, 5, 6 out for the 6 electrons as you put them in. These are the D electrons, the transition metals, all right? And if you count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 5 orbitals, 2 electrons per orbital, 10 electrons, and these down here are the F's. So the Aufbau diagram is what I try to push students to when they're brand new to chemistry, because you can figure out like 1S goes first, 2S goes next, 2P, 3S. But you can actually read the periodic table. If you know that the S's are on the left, the P's on the right, D's in the middle, and F's down here, you can actually figure all of these things out from the periodic table, which is kind of cool too. If you look at the numbers, 1S, 2S, 2P, notice how S's and P's have the same number, all right? That's the period number. So if you were curious what the last electron will be for francium, it would be a 7S. And it's not like I'm magic or anything. I'm looking at the 7, and I know that these 2 columns are the S block. Same thing for P block. Those are the ones on the far right over there. So that OG, radium, whatever it is, under radium, that would be a 7P electron down there. The D's and the F's aren't quite that number. Like the D's are this number -1, and the F's are that number -2. But hopefully you can begin to see there's multiple ways to figure out these electron configurations. You can always go back to the Aufbau, absolutely. But there's other ways to do it too. Any questions? Yeah.
Do we ever put helium on the left?
Oh, for this discussion, it really should be right here. But remember, helium is a gas, all right? And it's a super inert gas. Like, nobody has made any compounds with helium or neon, to my knowledge anyway. So that's why usually, Wes, it's over there on the right, all right? It's a filled octet, which is something we'll talk about here in a little bit too, all right? But really, for this discussion, it should be above beryllium. You're absolutely right. Sometimes these things kind of get a little spastic, so you have to use your imagination a little bit. Good. Other questions? Okay, so let's look at lithium, all right? We saw that hydrogen was 1s1. We saw that helium was 1s2. Lithium has a total of 3 electrons. It has 3 protons, but the neutral lithium would have 3 electrons as well. The first 2 electrons, 1s. All the s's hold up to 2 electrons. Then the third electron, 1s is filled. We then go to the 2s. So lithium would have a 1s2, 2s1 electron configuration. And notice if you take these superscripts, add them together, that's going to give you 3 total electrons. And that's a nice way to check yourself. This is an orbital box notation. I'm putting 1s at the bottom because that's the first one to get filled in. 2s, 2p, 3s, 3p. I'm going to put 1 electron in the 2s orbital right there. That's the third electron. Now notice that this up electron doesn't have a down, all right? That means that this is paramagnetic. It's got an odd electron all by itself. This is a diamagnetic pairing. You have an up and a down in the same box. This guy doesn't really do anything magnetic. But if you have even 1 electron by itself, you know it's going to be paramagnetic. And again, back to what Wes said, that was really cool. All the odd numbered atoms will be paramagnetic. Lithium here is odd, all right? More ways than 1, but anyway, odd number of electrons is going to be paramagnetic. Questions? Now, beryllium, right next door, has a total of 4 electrons. So it's going to have the same electron configuration as lithium plus 1 more electron. So instead of 1s2, 2s1, this is going to be 1s2, 2s2 for 4 total electrons. Atomic number 4, 4 total electrons, good to go. In this case, if you put the electrons down, all right, first 2 are in the 1s, and remember 2 s's are only 1 orbital, 1 room in those shacks. It's 2 electrons per s orbital, 1s2, 2s2, just as many up as down electrons. This one is diamagnetic. So earlier I told Wes that if you have to guess on the elements, guess paramagnetic. However, both helium and beryllium have been diamagnetic. But it's not just as simple as even electrons is diamagnetic, like we'll see. So hold tight. Now, moving on. Boron, number 5, 1 more electron. Now remember that the s ones will always hold 2. 2 electrons for 1s, 2 electrons for 2s. But when you get to p, wow, I need space all the time. Anyway, when you get to a p, like 2p, all right, p means L equals 1, and m sub L will be, I can't write and talk at the same time. If L equals 1, m sub L goes from negative L to positive L. So m sub L, negative 1, 0, and plus 1. Now each of these numbers is a box. So when you get to the 2p, you're actually going to write 3 boxes there because p's have 3 orbitals. S's had only 1 orbital, all right, 1 m sub L value that was allowed. But when you get to p, then there's 3 m sub L values and 3 boxes. So boron, 1s2, 2s2, 2p1, that's probably not too bad to figure out because you have 1 more electron than can fit in these 2. But the 2p looks a lot different because now we've got 3 boxes, 3 m sub L values, 3 orbitals. Last Monday I showed you some pictures how the p orbitals were like x, y, and z. All right, and that's the way you can think about these as well. And it doesn't matter if it goes in x, y, or z. Don't lose that kind of sleep. But on the other hand, that's why we have these 3 orbitals. So boron, 1s2, 2s2, 2p1, 5 electrons, an odd number. It's going to be paramagnetic as well. That single electron there is enough to make it paramagnetic. All atoms are, well, except for hydrogen, will have some diamagnetism in them, but you just focus on if they have odd electrons or not. Any questions? Yeah.
So how would, you said there was another magnetism that was like super magnetic?
Those are usually just for iron, nickel, and cobalt, and a couple of the transition lanthanides and stuff like that. We won't talk about the ones that make the ferromagnetic materials, all right? In theory, like even this guy, in theory, you could Jonah, but that's a little bit beyond where we're going to be and stuff, so good. Other questions? Now, Carbon is an atom with an even number of electrons. It has 6 protons, so that means 6 electrons. And Wes definitely saw that if the odd ones, if you have an odd number of electrons, it's going to be paramagnetic. But an even number of electrons can often mean paramagnetic as well. Now, for 6 electrons, you start off again, 1s2, 2s2, and you've got 2 more after that, 2p2, all right? 6 total electrons. This is the spectroscopic SPDF. But here's where this gets a little weird. Remember that the p orbitals have there's 3 orbitals per p subshell. And you really have like 2 choices. Like you could put an up arrow and a down arrow in the same box, or if I redraw them, you could put 2 electrons in separate boxes like this one, all right? And the punchline is, don't pair electrons unless you have to. So carbon is actually paramagnetic as well, because we keep electrons in their own boxes whenever it's possible. And I like to use the idea, like if you live in a house with a brother or sister, you'd prefer to have your own room, all right? You know, you've got your own music, you can watch whatever TV you want or whatever. It's better to have your own room if possible. And that's what happens with atoms too. You want to put electrons in their own boxes whenever possible. So this is an even-numbered atom, but it's paramagnetic. And that's why I said to Wes earlier, I said, if you have to guess on the periodic table, guess that most of them are paramagnetic. Hund, this guy, was the first one to figure this out. And Hhunds Rule just says, keep electrons in their own orbital as long as possible. When you have to start pairing them, then do so. It's a little bit of energy to pair them together. And, you know, just like anybody, we don't want to pay things. Well, we don't want to pay the energy required to pair them if we don't have to. And with Hhunds Rule, if you keep 1 electron per orbital as long as possible, you won't have to pay this pairing energy cost that happens. Questions? All right, so again, the punchline, you could draw carbon as a diamagnetic atom, but don't do it. That's Hhunds Rule. Hhunds Rule says put each electron in its own box as long as possible. And we will start pairing them up, but we only do that if we have to, all right? It's a little bit of energy to pair them up versus keeping them separate. So, nitrogen, 7 electrons, 1s2, 2s2, 2p3, 7 total electrons, 3 electrons in 3 orbitals. Again, don't pair anything up. Nitrogen is also paramagnetic. 1, 2, 3 electrons, each in their own orbital. That's the lowest energy configuration, the default configuration, and it's also paramagnetic. Now, on the next electron we add for oxygen, now we have to start pairing. To add an electron to 3s is a pretty good energy jump relative to adding a paired 2p electron. So when there's no more room, then we start putting the electrons together. But again, if you can help it, try and keep them apart if possible. Any questions on that? Okay, oxygen, 1s2, 2s2, 2p4. Again, count up the superscripts to get the total electrons. Once again, if you ever get lost. Excuse me, this is also paramagnetic. But notice here, that 8th electron, we are pairing it up now, all right? To go up to this box would take a lot more energy. So we will pair it up. So paramagnetic here, oxygen has 2 unpaired electrons. Nitrogen on the last slide had 3 unpaired electrons, but with oxygen now, we're gonna start pairing them up. So this one has only 2 unpaired electrons, but it's still paramagnetic, and this is another even one that's paramagnetic too. So that's why, again, a lot of the even ones are paramagnetic as well. All of the odd ones are paramagnetic, and a lot of the even ones are paramagnetic also. Fluorine, 9 electrons, 1s2, 2s2, 2p5. Again, count up the superscripts for the total number of electrons. We're going to pair up another electron. So notice here that for fluorine, there's only 1 unpaired electron. So we would put 1, 2, 3 electrons, 1 in each p orbital, pair up the 4th and the 5th ones right there to make fluorine. But fluorine is paramagnetic. And then finally, the next one, neon, one of the noble gases now, really inert, 10 electrons. 1s2, 2s2, 2p6. Now remember that with these boxes, each of those boxes is an orbital, and you can have a spin up and a spin down. So 1, 2, 3, 4, 5, 6. Neon now has every atom up has a down electron, or it's a diamagnetic atom. So now neon will be diamagnetic. It's super inert. It doesn't want to react with anything just like helium does. This is why they put helium usually on the right, because helium is also super unreactive like neon. Cool. Any questions on that? This way is a lot easier to write, but the orbital box notation is cool, especially if you're learning about the magnetism part. Yeah, Wes?
I think we said nitrogen, is that paramagnetic?
Para, that's right, yeah.
And then earlier we said that liquid nitrogen is diamagnetic.
Good observation, man. So nitrogen is one of the diatomics, and when you have paramagnetic nitrogen atoms coming together, they essentially pair up, so that paramagnetism goes away in the N2 molecule. Now, for oxygen with 2 unpaired electrons, you would predict that that would be diamagnetic as well, but you saw it stick there. Something going on with oxygen. So first of all, I applaud you for seeing that, because that's something that a lot of people don't see, so well done. Second of all, I think you can probably see why N2 would be diamagnetic, but oxygen being paramagnetic and not diamagnetic is something else altogether, and we'll talk about that next quarter. But again, well done that you saw that. I have a few more things to share with you besides the stuff in Chem 221. But anyway, well done. Very, very cool. It's the difference between individual atoms and the diatomic one. And the diatomic ones will oftentimes be different than the individual ones. Well done. Excellent observation. Other questions on that? All right. This is the end of the second period. Everything on the end of a period will be diamagnetic. So all the noble gases here, diamagnetic. Everything at the end of one of the blocks, so like these guys are the ends of the S's, those are going to be diamagnetic. And even the transition metals here at the end of those guys are going to be diamagnetic. So if you need to think about things like that, those are nice ways to kind of check yourself what's happening. This is a little animation showing boron through neon. And again, you can see how the electrons just keep getting paired up. But the important thing is this Hund's Rule. Keep the electrons in their own rooms whenever possible. Pair them up when you don't want to do it. You don't want to go to the 3s because that's a lot of energy. But literally, we're just adding electrons in. And again, each electron is there to compensate for an extra proton in the nucleus, that kind of stuff. These right-hand side elements, the 6 ones, are oftentimes called the p block because you're filling in the outermost electrons, you're filling in p electrons. This is the second period, so that's why these are the 2p's. The ones right below it, you'd be filling in the 3p's, etc., etc. All right, sodium is number 11. Now, sodium is the next period down. So we've been looking at just the first and the second periods left to right. Sodium's actually the beginning of the third period. Now, sodium has a total of 11 electrons because it has 11 protons. So to fill it in, it's not difficult. You can follow the off-bow, 1s2, 2s2, go down to the next one. The p's hold 6, so 2p6, but now we're going to be into a 3s1. So sodium, 1s2, 2s2, 2p6, 3s1. Now, these configurations get longer and longer, and you can tell it takes me longer to kind of spit it out. So one thing you can start using, which is awesome, is what they call noble gas configuration. 1s2, 2s2, 2p6, that was the neon core. And so what you can write this as, you can write it as neon in square brackets, 3s1. And this is sometimes an easier way to write these. Instead of writing out 1s2, 2s2, 2p6, 3s1, you can just write neon in square brackets 3s1. This is a nice shorthand notation that I recommend using. You don't have to, but it is kind of nice and stuff to break it down. They call this noble gas notation. You go backwards to the nearest noble gas, and you use that noble gas in brackets, and then anything outside of that noble gas, like 3s1 here, would go right there. An interesting thing happens. All of the group 1A elements, the 1A elements are the alkaline metals, so that would be lithium, sodium, potassium, etc. They all have a noble gas core NS1 configuration. So, I do not have enough truck space today. But anyway, we saw earlier that lithium was 1s2, 2s1, and 1s2 is the helium core. So we could have written this as helium 2s1, just like we saw that sodium was a neon core 3s1. Now, potassium is the next one down. Notice how lithium was next to 2, sodium is next to 3, potassium then would be 4. So you can say potassium, nearest noble gas, argon behind it, 4s1. This is kind of a quick and dirty way to find the electron configurations, and this works for all of the alkaline metals. So, let's pick the hardest one, all right, which is francium, all right? Francium is in the 7th period. If you go backwards to the nearest noble gas, it's Rn radon. You could write francium as radon, Rn, in square brackets, 7s1, because there's one electron inside. And that's kind of a nice, quick and dirty way to do a lot of these and stuff. There's patterns on the groups of the periodic table. Any questions on that? Aluminum is a group 3A. It's one of the quote-unquote twisted metals. 13 electrons. All right, well, getting to 2p6 was neon. 3s2 would be 2 more. So 10 plus 2, 12, that would be magnesium. 3p1 would be the configuration for aluminum. So the whole configuration, 1s2, 2s2, 2p6, 3s2, 3p1, which takes a lot of syllables and a lot of oxygen. 1s2, 2s2, 2p6 is just neon. So aluminum can also be written as neon 3s2, 3p1. If you do the noble orbital box, 3s2, 3p1, all right, all of the group 3As, with a small exception down here, will have some kind of core ns2, np1. Some of them are going to have a little d electrons. We'll talk about that here in a little bit. But what I'd like you to start seeing is that elements in the same group we saw had similar reactivity. Like I showed you silly videos of sodium, lithium, and potassium, rubidium. They were reacting with water, exploding, and stuff like that. Well, they have similar reactivity because they have similar electron configurations. They get more reactive as they go down because that outer electron really wants to get off, really wants to do something, all right? With lithium, it can sit there fairly well, but when you get down to the last ones down there, it really gets pretty crazy, so. Questions? Phosphorus, group 5A, 15 electrons, 1s2, 2s2, 2p6, 3s2, 3p3, or neon 3s2, 3p3. So again, noble gas configuration comes really handy as the elements start getting bigger. There's nothing wrong with writing it out like this, but after a while, when you're like, come on, Russell, something new here, noble gases are kind of a cool way to go. So here's the 3s2, here's the 3p3, all right? All of these 5As will have something similar. Some of them will have some Ds. We'll talk about that here in a little bit. But again, that's why they're all very similar in their reactivity. So chlorine, all right? Chlorine is number 17, all right? Chlorine is right there on the periodic table. And the question is, what's the electron configuration? All right. Well, chlorine is right next to argon. All right. It's not quite argon, but it's very close. And remember how getting to neon, it took 6 electrons? It'll take 6 p electrons to get to argon. And argon is in the 3rd period. So 3p6 would be argon. That means chlorine is going to be a 3p5. So one thing you can do on here is just look for some piece that has 3p. Well, there's a 3p. It's a 3p5. These have 3p6s. That would be argon or something like that. 1s2, 2s2, 2p6, 3s2, 3p5 is going to be chlorine. Now, if that's kind of like quack, 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 all right, remember you can also count the superscripts, and they should equal 17 if it's chlorine. So 2, 4, 10, 12, 17, that's 17 electrons. Either way you do it, you should be able to find then that answer B is the electron configuration for chlorine. And if you decide to write that as neon in brackets, 3s2, 3p5, totally cool with me, no problems at all. Any questions? Okay. So this S block, P block, D block, F block thing can be really helpful. And again, we already saw that the 2 left ones, which includes helium on this discussion, which is lame, I know, those are the S blocks because you're filling in S electrons. The 6 columns on the right are the P block. So really the main group metals, when we didn't use, Roman numerals usually and stuff like that, those are the S and the P elements essentially. That's what the ones, and the non-metals, Now, the ones in the middle are the D block, and these down here are called F block. All right, and so D and F block, D is the transition metals, and the F block's lanthanides on the top and actinides on the bottom. So you can use the periodic table to tell you electron configurations if you want. But I'm going to advertise once again, Aufbau will also tell you the order of these things. All right, you just follow the arrows up, and it will tell you what it is. So getting to 2p6, that would be neon. Getting to 3p6 would be argon, etc., etc. Transition metals involve d electrons, but one thing about the d's is that you have to backtrack a little bit to do the d's. Now, if you watch the Aufbau, it goes 2p, 3s, then 3p, but it doesn't jump to 3d, all right? Because of the n plus L rule, 4s comes before 3d. 4s has 4 plus 0, 3d, 3 plus 2, 5. So this is higher n plus L. So what that means then is you'll fill in the 4s electrons first, then you'll start doing the 3d. So on the periodic table, scantium is the first transition metal. It's on the 4th period. So potassium and calcium, you're filling in 4s electrons. But when you get to scandium, titanium, vanadium, it's this number minus 1, 4 minus 1. 3d1 would be scandium, and 3d2 would be titanium, etc. So then it says n minus 1. The n is literally the period number. And if you have a transition metal, it's always n minus 1. So that means that this first row of transition metals, iron, chromium, cobalt, etc., those are 3D transition metals. The next row down, molybdenum, ruthenium, rhodium, palladium, silver, those are 5 minus 1, 4Ds. These guys down here would be 5Ds, 6Ds, etc., like that. It's the period number minus 1 for them. Okay. So here's just some examples, all right? Potassium with 19 electrons has an argon core and 4s1 on top of it. Calcium is 1 more electron than potassium, so you would put that in the 4s as well. It would be argon 4s2 or 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now, scandium, 1 more electron. This is n minus 1. So this is the fourth period, 4s, but scandium 4 minus 1, 3d1. All right, so notice there how the d's, you jump back one in the n value just because of the way it works out. And then titanium, the next one, would be 3d2. Vanadium would be 3d3. I'm not going to go through all of these and stuff. Oh, this one. Notice here on chromium, instead of being 4s2, 3d4, chromium is 4s1, 3d5. Fascist chromium, Jonah, my favorite element too. Fascist chromium is not following the n plus L rule. What that means is that these beautiful rules, well, beautiful is subjective, these rules for n plus L, which work amazingly well for most elements, don't work for all of them. And chromium is the first one that's an exception. You would predict that chromium, with one more electron than vanadium, would be 4s2, 3d4. But in reality, it's 4s1, 3d5. These are breaks in the n plus L rule. And if I asked for the electron configuration for chromium, if you gave me 4s2, 3d4, I would be okay with it, because that's the predicted rule. The actual rule for chromium, the actual configuration, 4s1, 3d5. So what this means is that chemists haven't figured this all out yet. All right, there's still some problems with the rule. And for this class, if you give me the expected rule, 4s2, 3d4, or the actual rule, 4s1, 3d5, credit either way. Maybe one day we'll see the West analogy, the West extension to the n plus L rule, and it will explain why chromium is a free, no, excuse me, it's different than the other ones. And it's not just chromium, by the way, there's actually several ones that do this. Questions on that? Okay, so real quickly, manganese, copper is another exception, stuff like that. Notice how copper, you would expect, would be a 4s2, 3d9, but it's 4s1, 3d10, etc. Gets kind of crazy. So these exceptions pop up. Chromium and copper are the first ones, but there's several other ones, like rhodium is one of them, and I think palladium is another one. They pop up. I don't care for the stuff I ask you if you give me the expected n plus L or the actual values of them. But just realize the n plus L rule isn't perfect. There's another n plus L rule theory out there. It's called the Russell-Saunders scheme. It's not me, Russell. Darn it, but I like saying Russell because it sounds cool. Russell-Saunders is better for heavier elements, but it doesn't do too well for hydrogen and helium. And honestly, those are the ones we use more often. So Russell-Saunders isn't as cool as the n plus L rule, but gives me a chance to say Russell. Questions? Any of this stupidity? All right, so some of these elements don't follow n plus L, and chromium and copper are certainly the first two that don't, all right? They supposedly come from anomalies, so if you have a 4s1, 3d5, each electron gets its own orbital, which is supposedly more stable than having a 4s2, 3d4, but it's really not really understood why n plus L is breaking down sometimes. Again, all I really want you to know is how n plus L works. If you gave me 4s2, 3d4 or 4s1, 3d5, I'd be happy with both answers. You're seeing a limitation in the chemical theory as of right now. Question? Lanthanides and actinides are similar, except they have F elements. When you get down to the Fs, if it's n minus 1 for Ds, it's n minus 2 for the Fs. And there's exceptions to those two. So here's uranium and cerium. Like for cerium, you'd expect a 6s2, 4f2. It's actually a 5d1, 4f4. So there's lots of exceptions when it gets to lanthanides and actinides. The n plus L rule, once again, just kind of like breaking down. So just realize it's all stuff you can figure out. It gets a little funkier as you get into the heavier elements. This diagram shows the order. So you can see it goes 1s to 2s to 2p, 3s to 3p, but then 4s, 3d comes in between 4s and 4p, and then 4d, 5p, 4f before 4d, etc. like that. But again, Aufbau diagrams will share the same stuff with you. Any questions on that? Okay, this is a good place to stop. Let's take a 5-minute break, meet back here around 11 o'clock or so.